Let me illustrate the concept with the help of an example. Let's consider a round cross-section case. So we are having a tube of thin wall thickness. The mean diameter of this tube is given as small d, and the thickness is constant, which is given by small t. It is subjected to a torque T, and we have to find out the stresses and the angle of twist for this particular case. Now we know from classical solid mechanics that the governing torsion equation is given by T by IP equal to tau by R equal to G theta dash by L. I am using the notation dash in order to differentiate it from our notation theta, which is angle of twist per unit length, which is nothing but theta dash divided by L. So using this approach, we can directly find out the stress and angle of twist for the case which is given. Let's obtain the solution using the theory of thin box sections and then compare with the classical solution. Let me draw the figure once again. So we are having the tube of mean diameter d and thickness t subjected to torque T. As per the thin box section formula, the torque is given as 2Q multiplied by A, where Q is given as shear stress multiplied by thickness. So at any point, in this case, at every point the thickness is T, so the shear stress also will be constant, and multiplied by area. So here area is the one which is subtended by the mid surface of this cross section. So it is nothing but the area of this entire cross section up to the mid surface, which will be given as pi by 4 d square. So using this equation, we can find out that the shear stress can be given as 2T divided by pi d square T. Now let's compare the solution for the shear stress by using the classical approach. So in the classical approach, we are having T divided by IP equal to shear stress divided by R. Now IP in this particular case will be given as pi by 32 outside diameter raised to 4 minus inside diameter raised to 4, which can be simplified and written as pi by 32 do square plus di square multiplied by do square minus di square, which can be again written as do plus di and multiplied by do minus di. So we can simplify it as pi by 32. Since it is a thin section, this do and di, they both will be nearly equal to small d. So this is 2d. So this is 2d square. This is 2d. And do minus di is nothing but twice the thickness. So that is corresponding to it. So we'll get the value of IP as pi by 4 dq t. So that is the value of IP what we get. And hence, by this equation, we'll find out tau equal to TR by IP. So in this case, R and the mean radius both will be same. So we are considering R as d by 2, and we are having pi by 4 dq t. So we obtain the equation as 2t divided by pi d square t. So as you can see, the equation that we got exactly matches with the one which we obtained using the earlier, the thin box section theory. Let's now find out the angle of twist per unit length for this case. So I will draw the figure once again. We are having a tube of mean diameter d, thickness t, and is subjected to torque T. The angle of twist per unit length is given as Q divided by 2Ag multiplied by the path integral ds by t. Now Q is given as shear stress multiplied by thickness. A is given as pi by 4 d square. G multiplied by, now in this integral, since t is constant throughout the path, the t 1 by t can be taken out, so what remains is just 1 by t multiplied by integral ds along the mid surface path. So the length of mid surface path is nothing but the circumference, that is equal to pi multiplied by d. If we simplify this expression, you will get 2t by pi d square t after substituting the value of shear stress which we obtained previously, multiplied by 2 divided by dg, which gives us as 4t divided by pi d cube t multiplied by g. So this is the answer which we get by using the thin box section theory or by using the shear flow theory. Now let's find out the answer using the classical method. So in the classical method we are having T divided by IP equal to G theta dash by T. I am writing theta dash in order to make it separate from our earlier notation. So theta dash by L is the angle of twist per unit length which we are trying to find out. So using this expression we will get T divided by IP, we have found out from the previous page as pi by 4 d cube t equal to G multiplied by theta. So this gives us the value of theta as 4t divided by pi d cube tg, which is same as what we obtained earlier. So this illustrates how to use the thin box section formulae to calculate stresses and angle of twist for such problems. Let me further elaborate how to use the equation for the angle of twist, which is given as Q divided by 2Ag and multiplied by path integral ds by t. Let's have more discussion on how to compute this integral for some common sections. So let's consider a case where you are having a rectangular box cross section having different thicknesses, just to make the problem more interesting. So we are having a box section A, B, C, D having its mean surface dimensions given as width A and height as small b, horizontal one having thickness T2 and vertical one having thickness T1. And this box section is subjected to torque T. If we want to calculate the angle of twist, we need to evaluate this integral. So let's see how do we evaluate this integral for this particular cross section. For handling cross sections such as the one as shown here, we can break this integral into its subparts. So we can write this line integral as over the entire path ABCD as summation of the line integrals over path AB plus over BC plus CD and plus DA. And now we know that for path from A to B, that is from point A to point B, the thickness is going to remain constant. So the thickness would be given as T2, and the length of the path, that is ds by t. So ds by t is the length of AB. So this is nothing but length of AB, which is nothing but the value A. So this particular part can be written as A divided by T2. Similarly, the next part, that is from B to C, can be written as length of that path, that is small b, divided by thickness, that is T1, plus from C to D, it is A divided by T2, and plus D to A, which is B divided by T1. So in this fashion, we can calculate the path integral which is required in the calculation of the angle of twist. And just to reiterate, in this formula, the value of A is the area which is encompassed by the mid surface, and it is full area, that is this entire area will be value of A. So A in this particular case will be equal to small a into small b. So with this understanding, you can solve any problem related to torsion of thin box sections. Let me summarize the topics covered in this session. We have seen some practical examples where the theory discussed in this session is important for design of certain machine components which are of non-circular cross-section and are subjected to torsion. The major difference in deformation of non-circular bars subjected to torsion is observed in warping of its cross-section, which do not remain flat after loading, unlike that in the case of circular bars. The displacement-based approach can be used to obtain expressions for the stresses and angle of twist in terms of warping function, which is specific for a given geometry. We have also seen an approach based on shear flow which simplifies the stresses and deformation calculations for torsion of bars with thin box cross sections. I believe that this session equips you with an understanding about the theory of general torsion and gives you an ability to design thin box sections subjected to torsion. I hope you are benefited by this session. Kindly let me know if you are having any queries. See you again in the next session. Goodbye everyone.